Up to this point, we talked about permutations and combinations. In both of these scenarios, we didn't allow repetition, and that is called replacement, uh, which essentially means we disallowed using an element multiple times. What if we allow it? What happens then to the number of ways to do each task? Consider first sampling with replacement with order. Replacement is now allowed, so you can use you can use an element multiple times, and you have order. The order is significant. And the number of ways to choose r elements out of n with possible repetitions is n to the power r. This is simply due to the product rule. If you allow repetitions, for your first selection, you have n alternatives. This is selection number one. Selection number two, remember in permutations, when we disallow replacement, your population decreased to n minus 1. But now that is not the case because you allow replacement, which means you still have n alternatives. And in the third one, you again have n alternatives. It's all the way up to selection number r. You have n alternatives here, so you get n to the power r, a total ways to do this. In this case, of course, since the population is not diminishing, you can actually make more selections than your entire population. So we allow r greater than n in this case. So for instance, you can make 11 selections out of 5 elements if you allow repetitions. Simple as that. For instance, suppose that 3 friends are having lunch at a place with 10 different dishes. How many possible orders can they give? Now I have three friends, and they will make a choice out of 10. So I'm going to make 3 choices out of 10. The first friend, let's say, has 10 alternatives, but when the first friend makes the choice, that choice does not diminish the potential choices of the second or the third friends. They can still order those 10 dishes, so you can allow repetitions here. We have replacement. Multiple friends can select the same dish, therefore in total the number of different orders is 10 to the power 3. Now here order is important because, well, we define the order as which person, which friend gets which dish. If you switch them around, it's a different order. But that's from the perspective of the friends. What about from the perspective of the cook? When they order their meal at the table, the order is going to go to the cook, not in that way, right? Because the waiter is just going to say to the cook, okay, I need one of this dish, one of this one, and one of this one. Or maybe 2 friends ordered the same dish, so the waiter will say, I need 2 of these and 1 of this. The cook does not care which friend is going to get which dish. What is important for the cook is from which dish I need to prepare how many. That is the only thing that matters. So this is sampling with replacement, but without order. Now you do not care about the order. You just care about how many from each category. You now have categories, and here in this scenario, it's the dishes. The cook only cares about from each category, how many should I prepare? So how are we going to find the number of ways or the number of, let's say, possible orders in this scenario? We are going to model every category here as a container or as a box. And here you see I'm separating them. Since I have 10 dishes, I am using 9 separators. Okay, these are going to be my separators to denote my boxes, and I'm going to place 3 selections here in these 10 boxes. Okay, I can go like this, one here, this selection, another one, this selection, another one, this selection. But I can also do this one selection here and 2 selection here. You see, I'm not distinguishing between which person ordered which dish. That's not important in my eyes. Okay, I just know that I need to prepare 2 of this one and 1 of this one. That is what is important here. Okay, so repetitions are allowed and order is not significant. Or you can have this, all 3 orders the same. Or this one, for instance. Okay, so what should be the method to find the number of such orders? For this purpose, we use a representation that is called stars and bars notation. To represent the choices, and in our scenario we have 3 choices, we need R stars. We used stars to represent the choices, you see. And to represent the categories, for the n categories, I need n-1 separators. And those are going to be n-1 bars. So for 3 choices from 10 categories, some outcomes that we have seen earlier here, some of these outcomes, can be represented in this way. Now, for instance, let's look at these examples. This one I can represent as, well, this is empty here, so I'll start with a separator, then put an object here, and then a separator. This is empty, so do not put an item here. Put the next separator, and then put the selection here, and this separator here, and this separator here. These are empty. So this separator, and then this separator, and then put this item here, and then this separator, and finally this separator, and now I'm done. I have 9 separators and 3 items, 3 selections. Okay, so for this one I will have separator, separator, and then 2 elements, and then separator, another one, and then this selection, and then 4 separators. This is the representation we are going to use. Okay, so for this one, for instance, you have all 9 separators here, and at the very end, you have the 3 selections, which means all of them selected the final box, let's say. And now this representation can be actually represented using binary strings. If you represent bars with ones and stars with zeros, and these are the binary strings you have. And the common property of these is that all of them will have 9 ones representing the 9 separators, which correspond to the 10 categories, and 3 zeros representing the 3 stars, the 3 choices. Okay, now this is the problem of counting multisets. A multiset is a set where elements can be repeated, and essentially you are forming the multi-subsets, let's say, of a set which can be which can have 10 elements, but out of this you are actually producing multisets where elements can be repeated. The order is not important, is equal to A, B, A, but now you allow repetitions, which we call multisets. Okay, and this is known as the multiset coefficient, and this is the notation we use. And why is this equal to this? Because when you look at this representation, as I said, the common property of all these is that you have 9 ones and 3 zeros. So in total 12 bits, And out of the 12, 9 are going to be 1, 3 are going to be 0. So what you need is select 9 out of 12 or select 3 out of 12, and that's it. So this is essentially given by r plus n minus 1, and r here is the number of items, the number of elements. N minus 1 is the number of separators, because it's always one less than the number of boxes. Choose r or choose n minus 1. This is r plus n minus 1, choose n minus 1 also. Okay, so this is called the multiset coefficients, and when you have a sampling without order, with repetition, or with with repetition, you can use the multiset coefficient given in this way. And if in doubt, always refer to the stars and bars representation to set up what the items are, what the categories are, and then build the stars and bars notation. You don't need to memorize r plus n minus 1, etc. When you actually build the stars and bars notation, the scenario presents itself as just a combination. Now this one, since you have 10 categories and 3 selections, it's essentially 3 plus 10 minus 1, 12, choose 3, or choose 9. That's essentially it.